Welcome back for another deep dive. We've got a really fascinating one today. We're going to be talking about building machines with human-like intelligence.
Ooh, very cool.
Yeah, it's based on this article that you sent in called "A Path Towards Autonomous Machine Intelligence,"
Hmm.
and it's packed with ideas that will really make you think differently about AI.
Yeah, it's a real head scratcher.
It is.
Mm.
One of the first things that jumped out at me was this concept of the intelligence gap.
Okay.
The article talks about how quickly humans can learn, like picking up driving in just a few hours,
Right.
compared to the massive amounts of data and training that AI needs.
Yeah.
What do you think is causing this huge difference?
Well, I think it all comes down to this idea of common sense knowledge. Like as humans, we just kind of have this built-in understanding of the world.
Right,
Like
yeah.
we can predict what's going to happen, fill in missing information, and just generally make sense of what we see.
So, like a self-driving car might need to see thousands of crashes,
Yeah.
even if they're just simulations to learn that speeding around a corner is dangerous,
Exactly.
while a teenager just kind of gets it.
Yeah, they just kind of get it.
Yeah,
We intuitively grasp those concepts like physics, cause, and effect.
right.
And that's a huge advantage we have over AI right now.
It really is. And, the article talks about how this is like a fundamental thing that needs to be solved.
Oh, absolutely.
If machines are ever going to truly become intelligent, they need to develop something similar to this common sense knowledge.
Yeah, they got to figure out how to build that in somehow.
So how do we think intelligence develops?
Well, think about babies.
Okay.
They learn about the world in these stages.
Mhm.
They build up their knowledge layer by layer.
Like how so?
Well, it's fascinating how a baby goes from understanding that objects exist even when they're out of sight.
Object permanence?
Exactly.
Different.
Object permanence to grasping more abstract concepts like gravity.
Right.
It's amazing to watch them learn.
It really is. It's
Yeah.
like we don't just suddenly get complex ideas. They're built on this foundation of simpler ones.
Yeah, it's a process.
And the article suggests that maybe machines need to learn in a similar way.
That's interesting.
This hierarchical kind of way.
Yeah, like a step-by-step process.
Yeah. So speaking of design, the article proposes this new model for autonomous intelligence.
Okay.
They call it HJEPA.
HJPA.
And it's designed to mimic the way humans perceive reason and act.
So it's not just about crunching numbers and making calculations.
Right. It's about understanding how humans interact with the world.
And trying to replicate that process in a machine.
Exactly. It's really cool. They even break it down into modules that sound a lot like parts of the brain.
Oh, wow.
There's a perception module, a world model, a cost function, and even something called a configurator.
That's a lot of moving parts. So how do all these pieces fit together?
Yeah, can you give us a sense of how it all works?
Well, imagine it like this. The perception module acts like our senses,
Okay.
taking in information from the world around us. This data then feeds into the world model, which is constantly updating and making predictions about what will happen next.
So it's not just passively taking in data.
No. It's actively trying to figure out what's going on and what's going to happen next.
So it's like our internal understanding of how things work.
Exactly.
That's pretty cool. And that's where the cost function comes in, I guess.
Right. The cost function essentially guides the AI's actions by evaluating different possibilities.
So it's like the AI's internal compass.
Yes,
Yeah.
helping it decide what's good and bad or what actions are likely to lead to a desired outcome.
That's a really interesting way to think about it. And the article also talks about two different modes of thinking within this model.
Okay.
Mode 1 and Mode 2.
Mode 1 and Mode 2.
Can you explain what those are and why they're important?
Sure. So think about how you react when someone throws a ball at you.
Okay.
You probably instinctively duck or raise your hand to catch it.
Right.
That's Mode 1 thinking.
Okay.
Fast, intuitive, and reactive.
Like our autopilot mode.
Exactly. We don't have to consciously think about every little thing we do.
Yeah.
Then there's Mode 2 thinking, which is more deliberate and analytical.
Okay.
It's what we use when we're solving a complex problem, planning a trip, or making a difficult decision.
So Mode 1 is for quick reactions.
Right.
And Mode 2 is for deeper thought.
Exactly. And the AI model actually switches between these modes depending on the situation.
Wow. So it's designed to be flexible and adaptable, just like the human mind.
That's the goal.
This is all really interesting, but I have to admit, I'm still struggling with how this model actually learns.
Okay.
It's one thing to have all these different modules, but how do they work together to create something that resembles intelligence?
That's where things get even more interesting. The paper argues that prediction is absolutely fundamental to intelligence.
Meaning the ability to anticipate what's going to happen next.
Yes. And the way this model achieves that is through something called energy-based models, or EBMs.
EBMs.
It's kind of a different approach to AI than what we're used to. Well, traditional AI models often focus on recreating the input data as accurately as possible.
Okay.
But GP, which is the foundation for this HGPA model we've been discussing, works a bit differently.
Oh, interesting.
Imagine you're teaching a GPA model about the world by showing it a video.
Okay.
Instead of trying to perfectly reproduce each frame,
Yeah.
GPA focuses on learning the relationships between objects and events in the video.
So it's more about understanding the underlying patterns and dynamics.
Exactly, rather than just mimicking the surface details.
And that's a crucial difference because it allows the model to generalize and make predictions about new situations that it hasn't encountered before.
That's the power of it.
Wow. Okay, so instead of just learning to repeat what it's seen,
All right.
it's learning to understand the underlying rules of the world.
Exactly.
That's pretty amazing. But how does that actually lead to intelligence?
Well, the paper argues that by constantly trying to predict what will happen next,
Okay.
the AI starts to grasp fundamental concepts about the world.
So through prediction,
Yeah.
the AI begins to develop an understanding of things like object permanence and cause and effect.
Precisely.
That's a powerful idea. But JEPA is just one piece of the puzzle, right?
Right.
You mentioned HJPA earlier.
Yeah.
What makes it different?
HGPA takes this concept of predictive learning and adds another layer of sophistication,
Okay.
hierarchy. It allows the AI to learn at different levels of abstraction,
Yeah.
from simple to complex.
So it's like having multiple layers of understanding,
Exactly.
building from basic concepts to more intricate ideas.
Like, think about planning a trip.
Okay.
You start with a high-level goal, let's
Yeah.
say visiting a new city.
Right.
Then you break it down into smaller steps, booking flights, finding accommodation, making an itinerary,
Uh-huh.
and finally, each of those steps involves even smaller actions.
So HJPA allows the AI to approach problems in a similar way.
Yes, breaking them down into smaller, more manageable pieces.
That's fascinating. So we've talked about how this model perceives the world, makes predictions, and learns through hierarchy. But the real world is full of uncertainty.
Oh, yeah?
How does HJPA handle the unexpected?
That's a great question, and it gets to the heart of what makes this model so promising.
Okay.
HGPA incorporates something called latent variables,
Latent variables.
which allow it to account for the things it doesn't know.
So it's not just assuming that its predictions are always perfect.
Exactly. It recognizes that there's a certain level of uncertainty in the world,
Right.
and it factors that into its decision-making process.
Can you give us an example of how that might work in practice?
Sure. Imagine a self-driving car using HGPA to navigate a busy street.
Okay.
It might predict that a pedestrian is about to cross the road,
Uh-huh.
but it also recognizes that its prediction could be wrong.
Right.
So it slows down and prepares to brake just in case.
So it's being cautious and adaptable,
Yes,
rather
sir.
than blindly following its predictions.
That's the key.
That makes a lot of sense. But with all these different modules working together, it sounds incredibly complex.
It is. It's a very sophisticated model.
How does it all stay organized?
Well, that's where the configurator comes in.
Okay.
It acts like the conductor of an orchestra,
Right.
ensuring that all the other modules are working together in harmony.
So it's like the control center of the AI,
Yes,
setting goals, prioritizing tasks, and making sure everything runs smoothly.
exactly. The configurator plays a vital role in making the model flexible and adaptable.
That's really cool. This is all incredibly impressive, but I have to wonder,
Yeah.
are there any limitations to this approach? Does HGPA have any weaknesses?
Well, no model is perfect. One potential challenge that the article highlights is something called the slow features problem.
The slow features problem.
Okay.
Oh, that sounds intriguing.
We'll dive deeper into that in the next part of our deep dive, but let me just leave you with this thought.
Okay.
Sometimes what seems predictable can actually blind us to what's truly important. And that's something that even the most advanced AI models need to learn to overcome.
Wow. That's a great cliffhanger. I can't wait to hear more about this slow features problem and how it impacts HGPA, but for now, I think we've covered a lot of ground. We've gone from the basic building blocks of intelligence to a sophisticated model that can learn, predict, and even handle uncertainty.
It's a lot to take in.
It is, but it's also fascinating.
I agree.
I can't wait to see what the future holds for this kind of research.
Me too. It's an exciting time to be working in AI.
Absolutely. So we'll be back soon with part 2 of our deep dive, where we'll explore this slow features problem in more detail and delve into some of the other challenges and opportunities in the quest for truly intelligent machines.
Sounds good. I'm looking forward to that.
Me too. See you then.
And as we sort of jump back into this world of intelligent machines, Um, it's important to remember that we're exploring the very frontiers of AI research.
Oh, absolutely.
What we're talking about here has the potential to revolutionize how we think about and interact with technology.
It's definitely exciting stuff. But like you mentioned before, no model is perfect. We ended the last part talking about this slow features problem.
Right.
Can you unpack that for us a bit more?
Sure. So remember how we talked about JEPA learning by identifying and predicting relationships in data?
Hmm.
Well, sometimes those relationships can be a bit too predictable.
Too predictable? How is that a bad thing?
Well, think about it this way. Imagine you're training a JEPA model on a video of a busy street.
Okay.
It might become really good at predicting things like how the clouds move across the sky or how the trees sway in the wind.
Okay, I see where you're going with this.
Right.
Those things change slowly and follow predictable patterns.
Exactly.
But what's the problem with the AI focusing on that?
The issue is that those slow features can distract the AI from other more important information.
Okay.
The authors of this paper, Joint Embedding Predictive Architectures, focus on slow features, ran some experiments that really highlight this challenge.
Oh, I love a good experiment. What did they do?
They created this really simple environment with a moving dot against different backgrounds.
Oh.
Sometimes the background was random noise, sometimes it was a static image, and sometimes it was changing.
And what did they find? Did the GA models struggle with this?
Yes, the JP models excelled when the background noise was changing, because
Okay.
they could easily pick up on those patterns.
Right.
But when the background was static or less dynamic, their performance plummeted.
Interesting.
They were essentially fixated on the unchanging background and missed the moving dot, which was the key element.
So the AI got so good at predicting the easy stuff that it ignored the more important but less predictable information.
Exactly.
That makes sense. But
Yeah.
is this just a problem with JPAR, or does it apply to other AI models as well?
Well, the paper found that models using a reconstruction objective, like the popular RSSM, didn't fall into the same trap.
Oh, okay.
They were better at focusing on the moving dot regardless of the background.
So that suggests there might be ways to design AI models that are less susceptible to this slow features bias.
Yeah, absolutely.
Are there any proposed solutions?
There are. One idea is to feed the GA model with input that highlights changes over time, like image differences or optical flow.
So instead of looking at a static image, it's focusing on how things are moving and changing.
Exactly. This could help the model prioritize the more dynamic and potentially more important aspects of the environment. Another promising approach is to introduce even more hierarchy into the architecture,
Okay.
building on the HGAA concept we discussed earlier.
I can see how that could be helpful.
Right.
Breaking down the learning process into even finer-grained layers might allow the AI to better distinguish between those slow, predictable features
Right.
and the more important but less predictable events.
Oh, it's definitely an area of active research, and it'll be interesting to see how these solutions develop in the coming years.
So it seems like even with these cutting-edge models,
Yeah.
there are still challenges to overcome.
Oh, for sure.
It makes you appreciate just how complex intelligence really is.
It certainly does. And it highlights the importance of continuous learning and adaptation, not just for AI, but for us humans as well.
That's a good point. Speaking of learning and adaptation, the original paper also talks about this idea of a configurable world model.
Yes.
Can you remind us what that is and why it's significant?
So imagine you have a single, incredibly powerful AI model that could be configured for different tasks and situations.
So instead of having separate AI models for different things like playing chess, driving a car, or writing poetry,
Right.
you have one model that can do it all.
Exactly. It's almost like having a brain with different settings for different jobs.
That sounds incredibly efficient.
It is.
And I imagine it would also allow the AI to transfer knowledge from one task to another, right?
Precisely. The insights it gains from solving one problem could be applied to a completely different domain.
Wow.
This kind of cross-domain learning is something humans do naturally, and it's a key aspect of what we call common sense.
So if we can create AI systems that can learn and adapt across different tasks, we might start to see machines that exhibit more human-like intelligence.
That's the hope. And this idea of a configurable world model also raises some fascinating philosophical questions.
Oh. Tell me more.
The paper touches on the possibility that this kind of architecture could be the foundation for machine consciousness.
Wow. That's a pretty mind-blowing idea.
It is.
But I have to admit, I'm not sure I understand what machine consciousness would even mean.
Right.
Would it be like human consciousness?
That's a question that philosophers and scientists have been grappling with for centuries, and there's no easy answer.
Yeah,
But I think it's a question worth exploring.
definitely. It seems like we're on the verge of some truly remarkable breakthroughs in AI.
We are.
But with all this talk about machines that can learn, adapt, and maybe even become conscious, it's hard not to think about the potential implications.
You're right. As we develop increasingly sophisticated AI, it's crucial to consider the ethical and societal impacts. We need to ensure that these technologies are developed and used responsibly for the benefit of all humankind.
That's a conversation for another deep dive, I think.
Absolutely.
But for now, let's stick with the technical side of things.
Okay.
There's one more point in the paper I wanted to touch on before we wrap up.
Great.
It's the discussion about whether we even need symbols for AI to reason.
Ah, yes. That's a really intriguing point.
It is. For a long time, symbolic AI was the dominant paradigm.
It was.
But this paper challenges that assumption.
It does.
Can you refresh our memory on what symbolic AI is?
Sure. In a nutshell, symbolic AI represents knowledge and reasoning using explicit symbols and rules.
Oh.
It's like programming a computer with a set of instructions for manipulating those symbols.
So instead of trying to mimic the human brain directly, it's more about creating a system that can manipulate information logically, like a very advanced calculator.
Exactly. And it's been incredibly successful in many areas, like expert systems and game playing.
Right.
But symbolic AI has its limitations.
Like what?
It often struggles with tasks that require common sense reasoning or dealing with uncertainty.
Which are precisely the areas where the human brain excels, right?
Exactly.
So what's the alternative? How can AI reason without symbols?
The paper suggests that maybe, just maybe, we can achieve true reasoning through a process of energy minimization.
Energy minimization. I have to admit, that sounds a bit abstract.
I know it might sound a bit strange, but think of it like this.
Okay.
Imagine the AI's thought process as a kind of landscape with hills and valleys.
Okay.
The goal of the AI is to find the lowest point in that landscape, which represents the best course of action.
So instead of following a set of rules, the AI is like a hiker trying to find the easiest path down a mountain.
That's a great analogy. And the key here is that the model needs to be differentiable.
Meaning what, exactly?
It means that the AI can smoothly adjust its actions and predictions based on feedback from the world.
Okay.
It's constantly learning and refining its understanding through this process of energy minimization.
So it's like the AI is constantly feeling its way around this landscape,
Right.
adjusting its course as it gets closer to the lowest point.
You got it. And this allows for a much more flexible and adaptable form of reasoning compared to traditional symbolic AI.
But hold on, what about decisions that are more qualitative?
Yeah.
Like choosing which path to take at a fork in the road? That doesn't seem very continuous or smooth.
You're right. And the paper acknowledges this challenge.
Okay.
It suggests that in those situations, the AI might need to resort to mother search methods,
Okay.
like Monte Carlo tree search or dynamic programming.
So it's not a complete rejection of symbolic reasoning,
Right.
but more like an expansion of the possibilities.
Precisely. The authors are proposing a more flexible, adaptable approach to AI, drawing inspiration from how humans think. And, this whole discussion reminds me of another fascinating point in the paper.
Oh, I'm all ears.
It's the comparison between how AI systems learn and how humans learn through reinforcement learning. In a typical AI scenario, the reward signal is provided by the environment, like getting points in a game.
But that's not really how it works for humans, is it?
No, not at all.
We're driven by so much more than just external rewards.
Exactly. We have all sorts of internal motivations and drives that shape our learning.
Right.
And this is where the concept of the intrinsic cost module comes in.
Right. We talked about that a little earlier.
Yeah.
It's the part of the model that represents the AI's inherent motivations.
Right?
Things like curiosity,
Yeah.
desire to interact, or even a sense of pain when something goes wrong.
Exactly. And the paper suggests that by carefully designing this intrinsic cost module, we can guide the AI's learning in a more human-like way.
So instead of just chasing external rewards,
Yeah,
it's driven by a deeper, more nuanced set of motivations.
that's the idea. And that could lead to AI systems that are more creative, more adaptable, and ultimately more intelligent.
That would be amazing.
It would. But we've covered a lot of ground in this part of our deep dive.
We have.
I think it's time to shift gears and explore a really thought-provoking question that the paper raises towards the end.
I'm intrigued. What question is that? So we talked about building blocks of intelligence, the power of prediction, and even, that idea of machine consciousness.
Right.
What is this big thought-provoking question that you wanted to discuss?
Well, they bring up this point about the relationship between intelligence and embodiment.
Embodiment. Okay.
Yeah, like having a physical body.
Oh, okay.
So for a long time, AI research, has focused on developing this disembodied intelligence.
Right, like algorithms and things.
Yeah, like algorithms that can play chess or translate languages.
Uh-huh.
It's all about the software, the pure intellect.
Without having to deal with the real world.
Exactly. But this paper argues that embodiment might actually be crucial for developing true intelligence.
Well, yeah, I mean, humans learn and interact through our bodies.
Exactly.
Our senses, give us information. Our movements allow us to explore, and our physical experiences really shape our understanding of the world.
Yeah, and they're saying that by giving AI systems physical bodies, or at least simulating embodiment in a virtual environment, we might unlock these new levels of learning and understanding.
So instead of just processing data, the AI would be able to actually experience the world.
Yeah, in a more direct sensory way.
Learn about gravity by dropping stuff.
Exactly.
Understand spatial relationships by moving around a room. Maybe even develop social skills by interacting with other agents.
It's a fascinating idea.
It really is. Makes you wonder if all those years of focusing on disembodied AI might have been a bit of a detour.
It might have been, yeah.
It's definitely something to think about. And this whole discussion about embodiment ties back to our earlier conversation about common sense knowledge.
Oh, absolutely.
Because a lot of our common sense comes from our physical experiences in the world.
Right, like we learn that fire is hot by getting burned?
Yeah, you don't learn that from a book.
No, you don't. We learn that fragile objects break when dropped sharp things can hurt.
It's all about those experiences.
Exactly. And those experiences shape our intuition, our understanding of cause and effect.
Our ability to predict what's going to happen next.
Exactly.
So by giving AI systems the opportunity to have similar experiences, even if they're simulated, we might be able to help them develop this more robust and nuanced understanding of the world.
That's the idea.
Of course, there are still many challenges to overcome.
Oh, yeah.
Creating truly embodied AI requires not only sophisticated software, but also advanced robotics and simulation technologies.
It's a huge undertaking.
It's a multidisciplinary effort, for sure.
But the potential rewards could be enormous.
It's definitely an exciting area of research.
Yeah, to watch.
And who knows, maybe someday we'll be having a deep dive into the inner workings of a truly embodied conscious machine.
I would love that.
Me too. Well, I think we've covered a lot of ground in this deep dive.
Well, yeah.
We've gone from the fundamental challenges of creating human-like AI to the potential of prediction, the importance of hierarchy, and this fascinating idea of embodiment.
That's been a wild ride.
I have to say, it's been a real mind-expanding journey.
It has.
And I hope our listeners, have come away with a new appreciation for just how complex and how much potential artificial intelligence has.
I hope so, too.
Be sure to check out the links in the show notes if you want to explore some of the source material in more depth.
Absolutely. And keep asking questions.
Yes. Never stop learning.
The pursuit of knowledge is what drives innovation and progress.
Well said. Until next time, keep exploring, keep learning, and keep wondering about the possibilities that lie ahead.